Hi. So now that we've got a similarity solution for to study the boundary layer over a flat plate, I think the next obvious thing to do is to see whether we can take those equations which we developed, basically the boundary layer equations, and use it, right, for something which is other than a flat plate, I think, right? So let's sort of go ahead and do that. So we're going to basically term this the next couple of modules in this one, the similarity solutions to the boundary layer equations other than the flat plate, right? So this is also going to involve yes, some bit of derivations, but I hope that you kind of begin to get the nuances as we do the derivations, and there are some little elaborate ones which I will probably not do, but I will post them for you to look at, and of course any questions should be welcome. Okay, so your basic knowledge of calculus is something that we will look forward to. Okay, so let's get ahead and do that. So what I'm going to term this is similar solutions right to the boundary layer equations right. This is basically other than flat plate. Okay. Now let me sort of again write down the boundary layer equations which we will solve. So right, so that's the x momentum x momentum equation that contains information about the y momentum equations. So 2 rolled into 1, and this is the continuity equation, right? And we shall combine this with the boundary conditions that at y is equal to 0, u is equal to 0, v is equal to 0, and y at a far off place, right? So basically these are the dimensional form of the boundary layer equations, right? Okay, so let us let us begin. So let us say the stream function. Okay, let the stream function. So we're going to use a stream function, which is a 2D stream function. Yeah. So that u is equal to that, and v is equal to that, right? Now in this case, we're also going to use a coordinate. We're going to use a coordinate transformation. So we're going to write this okay, in such a way such that z is x by L, right? Which essentially means that if x goes from 0 to L, so z will basically go from 0 to 1, right? That eta is equal to y by L under root of RE, right? So essentially delta is a delta bar, is a function of zeta, so that which is essentially nothing but y bar by delta zeta. Okay, so this is a coordinate system that we will use. Okay, so like I said, so if I had a coordinate system like that, okay, so this is say 0 to L, right, and this is 0 to well, let's say delta bar, right? This is delta bar, this is, delta bar. Now here, so this is x, right? This is x goes from 0 to L, and the same thing, zeta is equal to 0 and zeta is equal to 1, okay? And when, this is actually, I'm going to write this as y bar, right? So y bar, so it goes from, so eta, right, y bar and zeta bar. So okay, let's put it this way. So 0 to delta bar. So this is my eta, right? So when y bar is 0, it is 0, okay? And when y bar is delta bar zeta, eta is equal to 1, okay? So let's just say here eta is equal to 0 and eta is equal to 1, right? So that's what we mean by transforming the coordinates, okay? Please don't confuse this with the non-dimensional form that we got earlier, okay? That was for a very different purpose. So, so that's what. So basically we're going to use this kind of a coordinate system. And there is yet one more thing which I would like to draw your attention to, because here the way we calculate the Reynolds number, it should be V infinity L by nu, right, rho v d by mu. Okay, so I got this v infinity and I also got this u infinity. Okay, let's not confuse the two. I'm going to take just an arbitrary kind of let me draw it here itself. Okay, I'm going to take an arbitrary kind of say a body. So for example, this is some kind of a body. Okay, this is some kind of a body, okay, and you have free stream which comes in, okay. Now this is v infinity, okay, and we will have flow like that, so on and so forth, right? Okay, and this is essentially u infinity. This is the u infinity that I'm talking about. And if I had a small axis system, so I would say that, so if I had something say like this right here, okay, that and this, so this is say y and this is x, then this is a function of x, right? So what we use, so the reason we're kind of differentiating all this, the reason we're writing all this is because now we're really going to talk about bodies other than a flat plate. So the geometry will play an important part. So we need to make the distinction about that. Okay. So hence this u infinity that we have everywhere, that we're taking everywhere, is really the localized velocity, and it's kind of the tangent to the surface at that particular point, right? And obviously, the surface of the body could be, anything else. And here's like two plates kind of, placed at an angle with each other. of course, you could have an airfoil shape like that, then the fact becomes different. Okay, so please, so again, if I had an airfoil, say if I had an airfoil like this, right? So you would still have V infinity coming in, and then at each point, for example, at each point, say, you would have something like that, and here you would have something like that, here you would have something like that. So that would be U infinity. So you can see that that is changing with x, right? Okay, so now having sort of gotten that, so let us go and there's just a little bit something. We're also going to look at some velocity. Okay, so okay. Okay, so let me kind of write this down a little bit for your reference, so that we make no mistakes so far. So the V okay, is the velocity, right, with which the flow impinges or say meets, right, the body, right, and this is the reference, or say this is basically V infinity. I'm calling it V infinity. Okay, I'm calling it V infinity. You can basically, it's a free stream velocity which meets the body, and this is the reference velocity to calculate Reynolds number of the flow. So this is the reference velocity to calculate the Reynolds number of the flow, right? Okay. Right, so once the flow is past a surface, boundary layer is formed, then U infinity x by U infinity etc. is used to denote the velocity of the outer flow. Okay, so yeah, so outer flow in the sense that now you have a boundary layer, so you have a velocity profile like that. So that will be a thing. So velocity in the outer flow is basically U infinity x. So that's what is used to denote that. Okay, so here I said small x or y. So in our particular case, so when we use similarity variables, so when using similarity variables, okay, un zeta, okay, is the velocity in the direction of z, is the velocity in the direction of z, or basically parallel to the z. Okay, like when I wrote down the z, so z basically goes from 0 to 1 and eta goes from 0 to 1. So un, right, so un basically goes from un1 to un0 to un1. So it's in the direction of zeta, right, and this can be said to be the same as the velocity of the outer flow, right. So essentially what I'm saying is that un zeta is equal to U infinity x, right. So which is, let me just write that velocity of the, when I say outer flow, I basically mean that now we do have a boundary layer, right, and this is the velocity just outside the boundary layer, which essentially is the free stream, right. It's just that the free stream, you have to take a component now of that free stream of V, isn't it? Because you have a body and we don't know the shape of the body. So, we have to define a new set of coordinate axis, which we are doing, right. Okay. So, now the way we will do is we did earlier, we chose a stream function and then we applied that and then we looked at the solution and the feasibility of that solution and whether that solution makes sense, right. So, that is really up to us. So, here too we are going to do that, right. So, therefore, basically what we are going to do now is say that we have a so having defined that. So, therefore, yes, so I did talk about the Reynolds number. Okay. So, that is that. Okay. Having come to that, so we are going to now look at a trial solution, right. What is the trial solution? So, we are going to write the stream function in terms of the zeta and eta, which we are going to write as L by under root R e, okay, u n zeta, okay, delta bar zeta, okay, and again this is the f of zeta and eta is the dimensionless stream function. Okay. In this case again is dimensionless stream function. Okay. All right. So, now that we have that, let us write down velocity, which is del psi and del y, okay, which is equal to del psi del eta del y, right. I think we have been doing sufficient mathematics so far for you to understand that. Okay. So, then, let me label a few things, right. So, let me label a few things. Let me call this as maybe 1 or something. Okay. Okay, let us go here. So, this is also something else. So, we have got, so basically what we are saying is, yeah, this actually that is fine. So, we will say we got an eta, okay, we got a z. Okay. So, let us call this as 1, this is 2, okay, and I am going to call this as 3. Okay. So, when I say delta psi, del eta, let us use 3, right, and if I do that, then what do I get? So, L by under root R e u n zeta delta zeta, right. None of that sort of changes. The only thing that really changes now, this is the one which is a function of eta, right. So, we get delta f, which is a function of zeta eta, delta eta, right, into delta eta delta y. So, if you go back here, yeah, so delta eta delta y. So, it is under root R e by L, right, into 1 by delta zeta, because that is also again not a function of eta. So, we will just write under root of R e by L delta bar zeta, that is all, right. So, under root of R e by L delta bar of zeta. Okay. So, if I do that, or u is equal to, right, u is equal to So we got this and this that cancels out. I got delta bar that cancels out, right? RE that cancels out. So what we basically left out, okay, let's do that, okay? So we got L and we got L that cancels out. Then we got RE and RE that cancels out. And we've got delta bar and delta bar that cancels out. So what we are left out with, okay, what we are left out with is UN zeta, okay, F dash, okay, F dash, and again all the derivatives here are with respect to eta, right, and F in this case is a function of zeta and eta, right. So if I get that, this, right. So we get a relationship for U, okay. Then again we will have a relationship. Again, probably I will skip a bit of steps and post the entire derivation on the web page, so you can take a look at it. I think you should get a hang of the calculus which is being used here. It's important. One of the things you could do is kind of do this, and so that you don't get lost or anything on the way. Okay. So the next step again is to do it for the V, right? And the V is essentially minus del psi del x, right? Or which is minus del psi del zeta del x, right? And if you see from here, del zeta del x, right? So del zeta del x is basically from 1, if you see, is 1 by L, right? Is 1 by L. So I can write this as minus 1 by L del psi del zeta. Okay, del psi del zeta. Now here, well, so basically what, if you use this del psi, so del psi del zeta, so you just del zeta of 3, right, 3. So if I do that, okay, or so I will just, what I will do is I will write this out, okay. So I will write this out, and what I will get is minus under root RE, okay, V, okay, that is equal to del zeta, okay, UN zeta delta bar F of zeta eta, right, and that's it. Okay. So minus RE into V is equal to del zeta of UN zeta delta bar zeta and F of zeta eta. Okay. So we get that, right. So once we get that, now this right hand side, let me skip that for now, okay. Let me skip that for now. You can basically, I will post this, right, but I think you should also give it a try yourself, okay. Give it a try yourself, but I will post this, for your reference, and you can take a look at the working out of the right hand side. Okay, so after having skipped that, so let me write out the final expression, so which turns out to be like this, okay. So, so basically V, okay, which is a function of zeta and eta, right, that is equal to minus 1 by under root R e, okay, del zeta u n delta bar into f, okay, plus u n. So this is u n, okay, this is u n, this is also u n, this is delta bar del f del zeta minus del bar del zeta eta f dash, okay. And please note that f dash, is a derivative with respect to eta, localized coordinates. Okay, so we get that, and I'm going to okay. So like I said, I will post this solution, the solution of the right hand side, the working out of the right hand side. So what I'm going to do now is, so now that we have v and u and v in 1 and 2, we're going to use this in the boundary layer equations, and what we get is something like this. So if we use so basically what we're doing is we are using 1 and 2, right, in the boundary layer equations, right. So if we do that, then what do we get? What we get is something like this, right, plus alpha 1 f double dash plus alpha 2 minus alpha 3 f dash square, okay, is equal to delta bar square, right, u n by v, this is the total velocity, f dash, this is basically v infinity, okay, f dash del f dash del zeta minus f double dash del f del zeta, okay, where alpha 1 is equal to delta bar by v infinity d zeta u n delta bar, okay. Alpha 2 is delta bar square by v infinity u infinity u n du infinity d zeta, okay, and alpha 3 is delta bar square by v infinity d u n d zeta, okay. So this, once we get, okay, so I'm going to call this, okay, this equation as 3, right, and this equation, as you can see, 3 here, it's a partial differential equation using f zeta eta, right. So 3 is a PDE for f this, right. Now what is interesting here is that what happens here is, this equation, as it were, the 3, is a PDE for f, right? But I would like you to think over this, that what if alpha 1, alpha 2 and alpha 3 are constants? If alpha 1, alpha 2 and alpha 3 are constants, right, then what happens to this equation, right? So, I think a lot of the times in fluid mechanics you encounter equations, which are quite rigorous and quite complicated, and but the moment you sort of break this down and you apply it to specific cases, specific physical problems, things become still become solvable. At least you get some inferences. Otherwise, the equation looks, the first question that comes to your mind, that how am I even going to solve this? Does this even going to mean anything physically? So let us come back in the next module and look at that and see that what are the possibilities of a solution from such an equation which we've developed, and whether it's even worth doing all of this. Okay, so I'll stop here for now and I'll meet you in the next one. Thanks.